Okay, here is an example of a flownet for a dam. Okay, this flownet may look very simple, okay, like a like a cartoon or so, but this flownet is actually drawn for a real dam. Okay, and something that I forgot to mention before and is very important is that the flownet and the geometry of the system, all of it, has to be drawn to scale. Okay, if you don't draw it to scale, then you will make errors making calculations. Sometimes it is a requirement to draw the flownet and the geometry of the system with a modified scaling. Okay, but we're not going to talk about that later. We're not going to talk about that now. We are going to talk about that later on in graduate courses. Okay, so here is the dam. It's concrete dam. Okay, the length of the dam into the board or into this paper is 100 meters. So the dam extends 100 meters into the page. Because it is so long compared to its height, look at the height, 14 meters, then we can use two-dimensional flow analysis, that is 2D seepage, Laplace's equation in 2D, to solve, to determine solutions or to get solutions for this example or this geometry. Okay? So the dam height is 14 meters, that is the height of the water behind the dam. The rock is down here. Okay, and so that is impervious. We assume that K is 0. Here's the K for the soil. So there's a soil mass, okay, over which the dam lies. The downstream is 2 meters of water above the ground surface. Okay, I'll tell you what this is in a little bit. And there's actually a wall below the dam that has been placed there to provide an obstacle for the water, so that the water doesn't have such an easy time going below the dam, but it has to go all the way down here to then come back up. Okay, remember the idea of a dam is to retain the water. So if the dam can pose as an obstacle or have another system that serves as another obstacle for the water flow or the water seepage, then that makes the dam highly efficient. This here is a filter, okay? This is some soil that is placed above the ground surface. It is a specific soil with a specific grain size distribution that is placed here so that the water doesn't take this base soil with it as it flows into the downstream. So this is called a filter. It prevents the removal of particles from what's called the base soil, which is this mass here. Okay? Now, you can see that the flownet is drawn, okay? And it looks like a very nice flownet. It seems that squarosity is maintained throughout, except in this element. This element is not fulfilling squarosity, okay? But for the purposes of this problem, we're going to assume that this is a correctly drawn flownet, okay? At the end, what you would do is essentially estimate the size of this element and compare to the other sizes, etc., to determine the appropriate or the true length of flow along that element. But for now, for this course, we're going to assume that this is a perfectly drawn flownet and that squarosity is maintained throughout. Okay, now let's count, because we need this later on, as you will see when you look at the other sides. Let's count the number of flow lines. Okay, here are 2 that are drawn. Look, 1 and then 2. So there's 2 drawn, and there are always 2 hidden. Okay, we know that there's one that is basically along the impervious boundary, so that gives us 3 flow lines, and the other one is a flow line that is marked by the interface between the structure and the soil that is subject to seepage. So the structure begins right there, Okay? So if you take a water droplet at this point, what would it do to get to this point? Well, it would go below the dam, along the surface of the dam, down the wall, along the surface of the wall, up the wall, along the surface, and then along this bottom of the dam until it gets to the filter. And we assume that the filter has such a high permeability or hydraulic conductivity that the water essentially escapes right there into the filter, and there's no flow net that extends into the filter. Okay, so notice that the flow net only extends to this location. It's all confined to the base soil. Okay, it doesn't go into the filter. Okay, so that is a flow line. The last one goes like this. And clearly it has to do that because equipotential lines cross flow lines at 90 degrees. Okay, so this flow line is crossed by all these equipotential lines 90 degrees, 90 degrees, 90 degrees, 90 degrees, 90 degrees. You see that? Okay, so we have 4 flow lines. How many equipotential lines? Well, let's see how many we have drawn. Typically we draw equipotential lines with with dash curves, as you see them here, and flow lines are just solid. So how many equipotential lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 drawn. 11 drawn. Okay? How many do we have hidden? We always have 2 hidden, the first and last. So, first, last. First and last. So we have 13. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, 11. 12, 13. Equipotential lines. Okay, so now we have counted the number of flow lines and the number of equipotential lines. Okay, after we have determined the number of equipotential lines and the number of flow lines, what we're going to do is we're going to determine the number of equipotential drops and the number of flow channels or flow paths. Okay, now let me put just an N here. Number of flow lines, number of equipotential lines, because that's typically what we use as parameters to denote this number of lines. Okay, the number of flow paths or flow channels. Okay, how do we call it here? I think we call this flow paths. Okay, remember, a flow path is it's a channel, okay, between 2 flow lines. Okay, we have 4 flow lines. 1, 2, 3, and 4. So how many paths do we have? Well, there is a path between this flow line and this one. That's this path here that constricts and then opens up. There's another one in here between this one and this one, right? And then there's another one between the one that goes along the structure and this first drawn one. Okay? That is a flow path. You can think of a flow path, the number of flow paths, as the number of flow lines minus 1. So we have 3. Okay? And then the number, sorry to have all the numbers up here, but the number of equipotential drops is also important. A drop is a step, okay, from one station to the next station along the marathon. Okay? So it's a step between an equipotential line and the next one. The first equipotential line is here. and the last one is here. Okay? So how many drops or steps do we have? Well, if we start here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 drops or steps. Okay? I'm not counting the lines, I'm counting the drops, the steps. From here to here, 1. From here to here, 2. From here to here, 3, etc. Okay? And there's 12. And you can think of the number of drops as the number of equipotential lines minus 1. 13 minus 1, 12. Great. Okay. Now we have the head at the first equipotential, the head at the last equipotential, number of flow paths, number of equipotential drops, number of flow lines, number of equipotential lines, and the delta H for the problem. Okay? Now we're going to pose the questions. Let's find what is the total head at point A. Let's find what is the pressure head at point A and the elevation head at point A. Let's find the same for point B. Elevation head, pressure head, total head, okay, for point A and point B. And we're also going to find the flow rate, the Q, for this problem, okay? What is the Q? The Q is the volume of water that gets to the downstream side per unit time. Okay, so that is a very important quantity that we need to design the dam itself. Okay, so this could be a dam that is drawn here, but it's not an existing dam, but it's a dam that exists only in the mind of the engineer. The engineer is thinking of this dam as one that he or she would like to construct. Okay, so he or she, the engineer, is designing this dam, and so he or she is saying, okay, I'm thinking maybe the dam should be this long, etc. It should be this high. Maybe the length of this wall should be about 8 meters. Okay, now I'm going to find Q for this problem. Okay, and see if that Q is an appropriate one for the owner of the project. Okay, or for the whatever the purpose of the dam will be. Okay, so let's find those parameters. Here is the solution actually in the next couple of slides. Okay? The delta H, as we said before, is 12 meters. Now here it says 14 minus 2. How did we get that? Well, 12 meters is correct. We said the head at the first equipotential line minus the head at the last equipotential line is the delta H. That's the most appropriate, correct, kind of a fundamental way to determine it. But there's another way, which is the kind of the short way, which is the elevation of this water table minus the elevation of this water table. So 14 minus 2 is the delta H, which is essentially that. Okay? But that's the shortcut. I would like you to do it in the first way we did it, because that way you actually are forced to determine the head at the last equipotential and the head at the first equipotential, and you're going to have to use those anyway. Okay? Alright. So, head at the first equipotential, we did it. Head at the last, we did it. Number of flow paths, we did it. Number of equipotential drops, we did that. Here's the equation for the flow rate for a 2D system. Okay? Very simple. Delta H, which we found to be 12. The length of the system into the page, what was it? 100 meters. Remember, this L is the length of the dam into the page. It's not the distance from here to here. This distance, which is the, let's call it the width of the dam, that you can determine using a ruler, because this is drawn to scale. So this is about maybe 15 meters or so. Of course, you would use a real ruler, not just your fingers like that, to determine the width. But the length, which is in this direction, is 100 meters, as noted here. Okay? So delta H times L times K which is the hydraulic conductivity of the soil through which seepage is taking place, and then this ratio, the number of flow paths, which is 3, and the number of equipotential drops, which is 12. Here's Laplace, because this is provided by the Flownet. Okay? So Laplace enters the calculation in here with this ratio. Here's the soil. If the soil has a low hydraulic conductivity, the Q is going to be low. If the soil has a high hydraulic conductivity, the Q is going to be higher, of course. They are proportional. Okay? The length, of course, and then the delta H. Clearly, if you have a very high head difference, which is what drives the flow, if this is very low and this is very high, then of course you can expect a higher or a high, relatively high Q. Okay, so you need to memorize this equation. Okay, again, the reason for memorization of some of the equations is because this has to be fresh in your mind, as I need to assume that you're going to be a geotech engineer when you graduate, okay? And even a civil engineer should be familiar, just a general civil engineer should be familiar with the most appropriate, or not most appropriate, sorry, the most fundamental equations for each field. Okay, and so if you perform the calculation, you will get, in this case, 0.3 meters cubed per second. You need to make sure that your units are kept in check, because here the K is given in centimeters per second. You need to convert it to meters per second, of course, to determine this Q, given that everything else, that is, these two, are in meters. This ratio is, of course, unitless, because even the parameters inside are unitless, 3 and 12. Okay? Cool. Next. Here what we are trying to determine is the heads at point A. Okay? So let's remind ourselves where point A is. In fact, let's look at this. Here's point A, right? Point A is on an equipotential line. So it's on a station, one of these stations along the marathon path. So when the water droplet goes from here all the way to here, it starts with 24 meters of energy, of head, right? And at this point, at the end of the race, it ends up with 12. So the question is, how many units of energy, that is, what is the head it has when it gets to this station? Okay? Here's where we have to think about the drops. Well, you can think of the drops as steps from one equipotential line to the next, right? That's what they are. One step, 2 steps. And something that is important here is that the energy lost per step is the same. So the water loses the same amount of energy or head from this point to this point as it does from that point to that point. Even though this element is very small and this one is large, the head loss from here to here, as the water droplet moves from here to here, flows from here to here, is the same as that energy loss that is suffered by the water drop when it goes from here to here, and from here to here, and from here to here, and from here to here, etc. Okay? That is the beauty of Laplace through the Flownet. So, how many drops do we have? We have 12. How much energy is lost throughout the seepage through all the drops? 12 meters. There's 12 meters lost in 12 drops. 12 meters are lost in 12 drops. 12 meters of energy. Sorry. This is what I wrote. 12 meters of energy are lost in 12 steps. Okay? So imagine the water droplet is running downstairs, and it runs downstairs 12 stairs, 12 steps. Okay? 12 stairs in a staircase. 1, 2, 3, 4, 5, 12 drops, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. So 12 meters of energy are lost in 12 drops. So in every drop, the water or the flow loses what? 1 meter. 12 over 12 is 1 meter. 1 meter of head is lost when the water goes from one equipotential to the next. That means that along this equipotential, the head is 23, because from here to here, if there's one drop, and there's 1 meter lost per drop. 24, 23, 22, 21, 20, 19, 18, 17, 16, that's here. 15 for that one, 14, 13, 12. Excellent, we can even check our answer, okay? Everything has to match so that when we get here, for this problem, the units of energy or head, the head at this point along this equipotential line has to be 12 as we had calculated before. Okay? So along the equipotential line where A lies, the head is 16 meters. 16 meters. So the head at A is 16 meters, the total head. Okay? And this is what we have here. The head at the first equipotential, yes, we know it. That is there just as a repetition of what we have at the top. But the head loss per drop is the delta H divided by the number of drops. The amount of energy lost over the number of drops, 1 meter. 1 meter lost of energy or head lost per drop. Okay? So, the head, we said, the head at A, 16 meters, right? Right there, 16 meters, 24, 23, 22, 21, 20, 19, 18, 17, 16. Along this whole equipotential line, any point, all points, or any point, has a head of 16 meters. All right, now, let's find the elevation head. Let's find all the heads. We know the total head. What is the elevation head? Well, if this is 2 meters, and this is the datum, and this is 10 meters here, then this is 8 meters. So the elevation head at A is 8 meters, if that's what we have here. Don't worry about this. This is the same as what we did before, actually, when we counted down 24, 23, 22, etc. Right? Essentially, what this says, let me erase the scratching out. What this says is that the head at A is the head in the first equipotential line minus 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6, 7, 8 drops times 1 meter loss per drop. 8 drops times 1 meter loss per drop. That's where this 8 comes from. Okay, so 24 minus 8, 16. We already know how to calculate it. That's what we got. 16, right? Okay. Now, we know the total head. We know the elevation head, therefore we know the pressure head, because the total head is equal to elevation head plus the pressure head. So if we know this one, and we know this one, then clearly this one is that minus that. And that's what it says here. Pressure head at A is equal to the total head minus the elevation head, 8 meters. Okay? Now, let's look at this. Let's look at this. Notice that at this point we calculated the pressure head to be 14, and at this point the pressure head is 12. At this point the pressure head is 8 meters. We just calculated it, 8 meters. The only way to calculate the pressure head at that point was to use the flow net and determine the total head, then the elevation head, and then subtract. Sorry, subtract here to get the pressure head. There's no way to get the pressure head calculate the pressure head at a point inside the flow net. I mean, how would you have guessed that the pressure head here is 8? If this is 2 and this is 14, there's no way to say, okay, it's somewhere in between, so 8. I mean, you could have guessed 5 or you could have guessed 10. So it is important to realize that any point inside the flow net or inside the soil that is subject to seepage, to determine the heads at those points, any point in there, you need to use the flow net parameters that we have obtained and do the whole calculation. The last head that you get in the calculation is the pressure head. You first get the total head, then you get the elevation head, and then you subtract to get the pressure head. With the pressure head you can actually get the pressure. Why? Because the pressure head times gamma water, 9.81 kilonewton per meter cubed, is the pore pressure. And the pore pressure in this case at point A is 78.5. 8 times 9.81. 8 times 9.81, 78.5. So that is the pressure, pore pressure at this point. The pore pressure at this point. Okay? Now, if we continue, we go to point B. Okay? Same. Head at first equipotential. Head loss per drop. Here we have calculated the elevation head at B, because the elevation head actually does not require any knowledge of the flow net or anything else. It's just the distance from the point to the datum. So it's 10 meters. 10 meters. That's the elevation head, right? The total head is obtained by using the flow net. Point B is on this equipotential line here. So 24, 23, 22, 21, 20, 19, 18, 17, 16, 15. That is 15 meters is the total head at point B. Or you can calculate it this way, it's the same. It's 24 units of energy, which is 24 meters of head minus 1 meter loss per drop times the number of drops to get to point B. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 drops times 1 meter is 9 meters. 24 minus 9, 15. Same as we got. It's the same. It's the same type of calculation. Okay. Now, the pressure head at B can then be calculated just like we did for A, which is the total head, 15, minus the elevation head, 10. So that's 5 meters. So the pressure, pore pressure at point B is that pressure head times gamma water, 49. 5 times 9.8, 5 times 9.81 is 49 kPa. Okay? And finally we get to uplift pressures for a 2D system, 2D flow system. Okay, remember that we talked about the case of no flow. That was a tank, okay, submerged in the soil, etc. And essentially what you have to find is the pore pressure along the surface, right? And that is the pressure head and gamma water, and everything's fine. But when you have 2D flow, then it's not so easy, let's say, or not so straightforward to determine the pore pressure. So what you need to do is the following. You draw the flow net, you compute the head at several points along the structure's base, and determine the pressure head at these points with the flow net, as we did for point B, and then we find the pressure at these points by the fundamental formula, which is the same as we did for point B. Why do I say point B? Because point B is a specific point that is located right there on the surface of the structure, between the structure and the soil, on the interface. The pressure obtained at this point, that we got as 49 kPa, That pore pressure is an uplift pressure because it acts at the surface, between the surface of the structure, between the soil and the structure. The pressure that we got here, 78.5 or so, yes, that is just a pore pressure like any other. It's not an uplift pore pressure. Okay.